Hello, and welcome to the webinar, Scaling Up Combustion Simulations on the Cloud, presented by Convergent Science and Rescale, where we will explore how to get quick converge simulation results on the Rescale platform, including how to set up, execute, monitor, and post-process converge combustion simulations, as well as custom builds and user-defined functions. Sorry if you heard a crash. I have a toddler in the background who apparently just dropped a bunch of toys on the tile floor right outside my door. But I am Jolie Hales, and I'm with Rescale, and I will be your moderator today. We also wanted to make you aware, my slide will change here. We also wanted to make you aware of the Big Compute podcast that's presented by Rescale, which shares stories about how engineers and scientists like you are changing the world through simulations and supercomputing. And the podcast was actually revamped a few months ago with a high production value storytelling kind of style, similar to Radiolab, if you're familiar with Radiolab. And recent episodes explore everything from supersonic jets like Boom Supersonic to simulations of tsunamis to Mars rovers to simulations of COVID aerosol particles and which musical instruments are the most dangerous in terms of being contagious, and everything in between. The podcast is getting a lot of praise and popularity. It is fast climbing the charts. So we do invite you to take a listen anywhere you get your podcasts or on bigcompute.org. All right. Also, if you have any questions as we proceed with this webinar, feel free to write any questions that you might have for any of our presenters in that questions window that you should see on probably the right-hand side of the GoToWebinar interface. And then we'll take a few minutes to answer those questions at the very end of the webinar. So after both presenters have given their presentations. Don't be shy. Feel free to ask anything that you need answered. And without further ado, we'll go ahead and get started. Our first presenter for today, I've got to say, out of about 2 decades of professional emceeing experience, our first presenter today takes the cake for the most awesome and challenging name. So this is that I've ever introduced. Samira has a great sense of humor because I know I'm going to slaughter this, but Samira Vijayakulasuria. So I hope I got that somewhat right. But he's awesome. He's a senior principal engineer at Convergent Science, and he has been with the company for nearly 10 years, and he's leading the internal combustion engine application support team. And he's a key resource for Converge support globally. And Samira received his PhD in mechanical engineering from Purdue University and currently resides in Madison, Wisconsin with his family. So we're happy to have him with us. Also, after Samira, we'll hear from Nithin Jacob, who is a customer success engineer at Rescale. And Nithin is based out of Boston, and he's responsible for ensuring Rescale customers have a positive and successful adoption of the Rescale platform as they embark on their cloud HPC journey. He has a master's in mechanical engineering from Arizona State University and 6 years of experience in the CAE industry, supporting engineers and scientists with automotive, medical device, and manufacturing sector needs. And when he's not working, he enjoys photography, table tennis, soccer, and kayaking. Always fun to hear what people like to do when they're not on a webinar. So at this time, I will go ahead and turn control over to you, Samira. So you should see a window pop up that gives you presentation control.
Wonderful. Good afternoon, everyone, or like good evening, good morning, wherever like you guys are. I'm Samira Vijayakulasuria from Convergent Science, and I'll be presenting the Converge part of the this webinar, which we're going to talk about combustion, specifically onto internal combustion engines, and how scaling works with Rescale. So Convergent Science as a global presence. Head office is in like Madison, Wisconsin. As this slide shows, we have presence in a lot of the other countries, Europe, Asia as well. Rescale has been a valuable partner for Convergent Science for many years, and you'll see why Converge and Rescale works pretty well to bring you kind of the best product in the market when it comes to your IC engine combustion simulations. We have many collaborators as well. Different national labs throughout the world partner with us and work hand in hand to bring you one of the best softwares available for your IC engine simulation. Now let's take a minute to look at why we need superior scaling. Why can't we like simply run on few cores, if not like serially? I think like all of us here understands why not, because we want to simulate complex multi-physics simulations. We want to do more and more better simulations. And as computer hardware and computer software marches like front, there's a need for the computer software side to actually harness the capabilities of computer hardware and which actually ensures a faster run times, and that finally transforms into rapid prototyping of your designs. Now, even though this webinar is on IC engine combustion simulations and how you can use supercomputing clusters like Rescale to scale your simulations very well, Converge is also a general CFD code. It can be used for general CFD as well. And I'm showing here some of the applications other than combustion, IC engine combustion, that you can do with Converge. You can see here, I'm not going to list out everything, but you can see some screw compressor applications, pendulum pumps like to biomedical applications. Now, Converge also is like really good for like combustion simulations, not only for IC engines, but like we started like our journey like in Converge like with IC engines, but it has quickly grown up to encompass all types of combustion simulations. You can see here IC engine simulations, gas turbines. They have applications not only in terms of like favorable combustion, where we want to optimize combustion to get to harness power out of that, but in order to we also want to model combustion so we can mitigate combustion, like in electric battery thermal runaway simulations, or fire safety in oil and gas kind of applications. Now, let's look a little bit more into why you'd want to use Converge for combustion modeling. We offer you a rich suite of combustion models, including a detailed chemistry solver. It parallelizes excellently with the CFD and combustion solvers. And that parallelization, the individual parallelization, or I would say independent parallelization, saves quite a bit of like time. And Converge offers you superior scaling, and that's what this webinar is about when it comes to your combustion simulations. And you can see on the right-hand side, this figure shows a combustion in a burner simulation. So if you're familiar with Sandia Flame D, it's a widely available combustion case from like Sandia National Labs. So in this simulation, we have 170 million cells, no AMR like or adaptive mesh refinement being used, but you can see up to about like 8,000 cores, it scales near perfectly. Now let's move a little bit on to IC engine specific. Like, so we talked about like why you'd want to use Converge for combustion, because it has many features that you would want, many models that you would want, and you would and it has like superior scalability and parallelization. Now let's look into combustion in IC engine specific and why you would want to use Converge for that. I'm showing here different applications. These are not the only applications that you can use to, like you can use Converge for. There's many applications, as long as you can mathematically model the combustion chamber or the engine itself, and you'd want to model combustion, Converge is your tool of should be your tool of choice. We are the market leaders in IC engine modeling. Approximately 80% of the engine makers in the world uses Converge. You can see on the chart on the left, many engine makers in US, Europe, Asia use Converge as their tool of choice. So why would you'd want to use Converge, and why do we have so much success in IC engine market? Several reasons, and let's try to quickly go through some of these reasons over here. We offer you fully automated meshing, so you as a user do not have to mesh before you run your simulation. Converge takes that burden out of you. We do the meshing at runtime, so there's zero user meshing time, and there are no caveats in here. There are no catches in here. Adaptive mesh refinement. It's a method to automatically resolves the engine flow when you inject fuel, when there's flame propagation due to combustion, or automatically at a lower computational cost. So you don't have to think about where should I put more cell resolution, or where should I remove cell resolution so I could actually run faster. Adaptive mesh refinement, or AMR, takes care of that. We have several advanced features that are quite important for a typical IC engine simulation today, such as internal nozzle flow simulation. We have dynamic mechanism reduction, where the mechanism, you can start off with a larger mechanism and it reduces dynamically when the simulation is taking place. We offer you the optimization, where you could actually optimize your operating conditions, not only that, your geometry as well, using genetical algorithms. Our detailed chemistry solver is called SAGE. It can be used with any number of species. So it works well with large mechanisms as well. When I say mechanism here, what I mean is the kinetics mechanism, where you have your gas phase species and reactions. As long as your mechanism supports it, as long as your mechanism represents it, you can use any number of fields. So the multi-field modeling is very, very easy in Converge. There are other combustion models as well, which are much more simplified than detailed chemistry solver. So if you are interested in modeling emissions, you can use detailed chemistry. If you are simply doing a thermal analysis, you want simple heat release from combustion, you can use some of these simplified combustion models to run faster. And Converge has conjugate heat transfer modeling, where you can do thermal analysis, modeling your water jacket simulations, like your engine head, piston, likewise. And we offer a rich suite of emissions modeling capability as well. If you are using detailed chemistry and your emission species, the evolution, the production, and the destruction of those chemical species, the emission species, are in your mechanism, then it's automatically taken into account. But some of the species like soot, we have different models available as well. Spray and combustion is also important when you talk about IC engine combustion. You need to represent your spray very well, and some of that goes even upstream of the combustion chamber into the injector, where the modeling of the flow, the fuel flow inside the injector with the needle moving up and down, not only up and down axially, but even the needle wobble being taken into account. All of that can be very easily done in Converge because of the automated meshing, and then the adaptive mesh refinement, scalability, parallelization, all of that helps in here. Converge offers you volume of fluid approach as well, where if you want to model the fluid flow, the fuel flow as in Eulerian phase rather than in a typical Lagrangian fashion. Now let's look at some scalability information. Converge 3.0 is our newest version, and it has a lot of enhancements when it comes to scalability, running on like hundreds to thousands of cores. The memory the memory footprint is low, and how we store surface across cores is improved, and the final product is you have a much more scalable code. Now, when the scalability actually improves when you are modeling large simulations, meaning millions and millions of like cells. And if you are simulating smaller problems, like let's say in a diesel engine simulations, you're only doing a 60-degree sector and your cell count is somewhere around like 100 to 200,000, you would still get a benefit of using hundreds of cores, but that would quickly diminish, because now instead of having 20,000 cells per core, you are into like hundreds of cells per core. Now the communication time is going to like, hamper the performance. So you always have to like, keep in mind, you can't simply throw out like thousands of cores to small problems and expect it to give you better behavior. You need to understand there's this competing effect of communication time. So I'm showing this like diesel engine sector case, which is a smaller case. Cell count is somewhere around like 100 to like 200,000. We ran this on an older version, which is 2.4 given on the second column. The newer version, which is on the third column, on the same number of cores. You can see we get like marginal uh, performance improvement, but it still improves. So you are better off like using this newer version. Now I want to like show you a larger case, a full engine case, not a sector, with the intake and the exhaust. We haven't like we are using adaptive mesh refinement. We are using spray combustion. This case essentially is a typical IC engine case, which is not tuned to give better performance in terms of scalability. So this is a case that how you would actually run it for your production run. This case has about like 1.3 million cells in the max, and minimum it goes to 230,000. And it was run in a like internal cluster, and Nitin, who's going to talk like after me, is going to show the similar case on Rescale. So you can see, you can compare the powerfulness of Rescale clusters as well. Now, one thing I want to like emphasize before I show you the data is the interconnect. With the newest version of Converge, for you to harness the advantages of the scalability, you need to have a faster interconnect. Now, it has a lot of information on this. So essentially what we have done here is we have taken that previous case and run it on 56 cores up to 448 cores, the first column on the table. Now on 56 cores, it takes like 11 and a half hours. And on the far right-hand side of the table, you have engine cycles per day. That means if you ran it on 56 cores, you can only run 2 engine cycles per day. Now look at the last row. If you run the same case on 448 cores, you can actually get about 12 engine cycles per day. So now this is actually huge in terms of like engine simulations, and using engine simulations to do predictive modeling and then design. Because what this says is like if you have access to 448 cores, and if you run in one of your engine cases, before it took like 11 and a half hours, now it takes less than like 2 hours. So before, if you could only run an engine case for just 2 days before you had to get into your analysis, so you were actually doing just 2 cycles, just like 4 cycles, and then trying to like guess or like use your best judgment to find answers on that, what you need in terms of your design from that 4 cycles. Now, with the superior scalability, you're at like, 48, you have 48 engine cycles run in just like 2 days to give you the data that you want. So this is like, think of this as a virtual test bench. Now you could, if you want to average it, you can average the 48 cycles and like look at different designs. If you want to look at cycle to cycle variation, you can look at it in that. But your statistics, like from your cycle to cycle variation analysis, is going to be much better, because now you have more samples to draw your statistics from. So that's the powerful nature of Converge 3.0 when run on multiple large number of cores. So with that, I thank you, and I would let Nitin take over for the Rescale part. And if you have any questions, please type in the questions window, and we'll definitely answer those at the end.
Perfect. Thanks, Jolie and Samira. Very, very interesting first part of the webinar. So for the second part, the remaining part of this webinar, we'll actually be focusing on, how the Rescale Intelligent Computing Platform is enabling, Converge 3.0 users such as yourself to scale those internal conversion engine simulations on the cloud, right? So Samira touched base on that, the ability to run on massive, cluster sizes and bringing down your simulation time per engine cycle means you're able to run a lot more engine cycles in the same time and optimize your simulations. So we will also jump on a demo to take a look at how we can run that same port fuel injection model on the platform, right from inputs to actually post-processing the results using a Converge Studio on the platform as well. So let's actually jump into it. So for those of you who are new to Rescale, just want to give a quick background. The company was founded back in 2011 by 2 former Boeing engineers. During their time at Boeing, they were actually able to take advantage of utilizing unused HPC hardware resources over a weekend to actually run massive distributed, optimizations for the Boeing 787 wing design. And this accelerated their product development and innovation. And it was actually with this thought, this small project, that actually the company was founded. And since then, we have now grown to serve greater than 200 plus enterprise customers, primarily in the Fortune 500 space. So what we have done is we have partnered with all the major hardware providers, be that cloud providers, as you can see in the list here, AWS, Microsoft, Google, or even bare metal providers such as IBM, Oracle. And on the other end, we have partnered with all the major HPC software providers, such as Convergent Science that we have here. So really enabling users to have the seamless experience to run all these different tools on all these different cloud providers or on-prem hardware without any of the complexity that comes with it. And finally, from a company standpoint, we're headquartered in San Francisco, and we have global offices in EU as well as in Asia Pacific. From a market segment, today we cover anywhere that science and engineering R&D work is being done. So that's anything from aerospace, automotive, for those combustion simulations. We have a lot of customers use Converge, and everything all the way to public sector as well as academia. So that's a quick overview of Rescale as a company. So now let's double click a bit more and see how does Rescale actually enable intelligent computing, right? So what does that mean? So in a nutshell, what Rescale is an intelligent SaaS platform. So we are a software as a service platform, which acts really as this control plane, right, between the hardware and the software layers. So users, again, have that seamless interface to run their Converge 3.0 combustion models on a variety of optimized and tuned HPC architecture. So again, what you see at the bottom here is the infrastructure layer, which is thanks to our partnership with all the major infrastructure providers, both on the cloud space. You can see AWS, Azure, Google. On the bare metal space, we have IBM, Oracle, as well as the legacy on-prem providers as well, the Dell and the HP clusters. On the top, you can see the application layer, which in this case is Convergent Science and Converge 3.0 specifically. So that's a software side of things. And again, like I mentioned, Rescale sits in between these, and it acts as the control plane that's able to orchestrate the entire workflow end to end. So you can see some of the intelligence highlighted here. On one end, you can see that, as an engineer or as an engineering manager, you're able to optimize your HPC needs, right? Make sure that, hey, as an engineer, I'm taking advantage of, whatever latest and greatest hardware I have at that time. And also that I'm, utilizing the right options, the right costs to meet my, product development, my product innovation needs. On the other end, you'll also see that from the business standpoint, the business leaders are able to, from your organization, they're also able to match what they want from like a cost perspective, their business, goals. They have policies around that they can even control independently on the platform. So that gives you the complete flexibility, but from both from the engineering standpoint as well as from the business standpoint. So then just going a bit more deeper into that simplified diagram of that HPC stack that you saw. So if you have previously, managed or used HPC clusters, even if it's a very small cluster that you have locally, then you are most likely aware of the various complex parts that need to be configured for that environment to be set up right and actually, run those jobs that you're interested in. So what Rescale does is actually, we saw that control plane, right? So what we're doing is we're automating and taking over that responsibility of managing this entire HPC stack. So that in turn provides a modern HPC experience to the users, right? So every box that you see here has an opportunity cost associated with. Every blue box that you see here is where Rescale comes in and manages the entire environment. At the bottom, again, you can see our integration with the cloud providers, as well as the on-prem hardware providers. So we have that unified API interface to work for both hybrid as well as multi-cloud operations. On top of that, you have the R&D workflow automation, operations management, and again, like I mentioned, the ability to do, policy-based controls of who is using what and what resources they are using on the platform. On top of that, we have the application lifecycle and license management. So as we saw in the previous slide, we have close to 600 plus tools today, all converged tools, convergent science tools being part of that on the platform. So we manage that completely for our customers. And we also have licensing options, right? Convergent Science is actually one of our partners, which actually also provides on-demand licensing. So you get the complete flexibility, and we'll look at this in the demo of running your jobs, paying per cost, per job to run both hardware as well as software. Now, yeah, so then touching base on the left, you can see, again, going back to the various controls, you're optimizing your HPC environment to meet your capacity needs, your performance needs, right? Hey, is my engineers using the right version, the right tools? Do they have intelligence on, what software they're using and what hardware is optimized for that specific software, right? So how are we actually providing this intelligence? With every job that, a customer is running on our platform, we have all this metadata on how they're using the jobs, right? So what we are doing is we're packaging all that data and providing it back to the customer so they can make more informed and more, intelligent decisions around what they should use and how they should use it on the platform, always optimizing for, both performance as well as cost. Then coming to the right-hand side here, you can see the security stack. So obviously, when there's any kind of data transfer, security is of high importance. So we have a full stack of security and compliance standards. So you can see all the major compliance standards like FedRAMP, ITAR, HIPAA for medical data, SOC Type 2 certified. So we have all those certifications, along with the fact that we are encrypting all your data both at rest as well as in transit. So anywhere the data that you're pushing to the cloud is always encrypted. So what this means is, at the end of the day, the users, such as you, the engineers, the scientists, they are only exposed to this part of the HPC stack, right? So all they need to, spend time on is, running their open source applications on the platform, running their commercial ISV applications such as Converge 3.0 on the platform. Or today we also support, bringing your own containers and bringing your own workflows, custom workflows that you can easily onboard. So this really gives the engineering team, the engineers, complete flexibility on how they want to utilize the different aspects of the cloud without any of the complexity, right? So we abstract everything below this user application layer, away from the users, away from the engineers, so they only spend time on that. So I hope that gives you a bit more understanding about how the platform is orchestrated and how it's able to use the data to provide intelligent decisions to the customers. So now after all this, why do you actually need a modern HPC experience, right? So why should something change now? So let's take a walk through the last 6 decades, right? So in the 1960s, the 1980s is when the hardware systems came into play. Like we had the big players like Cray, Dell, IBM, and mainframe computers and supercomputers were handling data processing, and that actually transformed the industry quite a lot. Now, digital transformation's impact on business workloads in the 2000s are commonly celebrated. So we all know about VMware, which came out with virtualization of machines. All the cloud providers such as AWS, Azure, Google Cloud, uh, they all came in the 2000s to enable these business workloads, right? So if you think about business workloads like your business applications, they usually require commodity hardware, just virtualization and some amount of open source softwares, right? So these were the key enablers, and combine that with the emergence of cloud in the 2000s, the business technology stack is completely automated, right? And today it's already available on demand for any enterprise or even startup customers that need it. So that's why we can already see 80% of the cloud. When we look at data internally, we see that almost 80% of the business workloads are already in the cloud. Now, for R&D, for HPC needs, it's a very, very different story, right? Because primarily, it relies on a much more complex stack. So, for example, R&D workloads require specialized HPC architectures, which are specific to the way different tools are run, right? So, as Samira mentioned, right, if you're running these large simulations and you want to scale them across multiple nodes, then you want to use some kind of hardware which has a high interconnect speed, so you're not losing any time with all the communication between the nodes, right? So digital R&D, HPC needs, they come with a more complex requirement of HPC architectures. The ISVs such as Convergent Science, they have been onboarding, they have been increasing their ability to run on the cloud. So that's as we can see here today. So these are some of the challenges, and that's one of the reasons we only saw around 20% of the workloads for HPC is actually now starting to be in the cloud, right? So there's a huge opportunity there. Now, the good news is that R&D transformation in each of these challenges now have solutions, right? So first, cloud providers are aggressively adopting new hardware architectures which are specialized for HPC. So today, our study indicates that we have around 300 architectures available from cloud providers which are specific to HPC needs. Secondly, ISVs such as Convergent Science have actually increased their role in the cloud. Convergent Science, like I said, is one of our ISVs who partner with us to bring on software on demand, pay-as-you-go licensing option. So it gives you complete flexibility, and full stack solutions like Rescale, we believe, will provide you the R&D computing as a service that will empower your R&D department and IT with control. So with that, moving a bit further, so what does that mean for a traditional user, right? At the end of the day, what that actually means in day-to-day usage, right? Traditional computing, usually users will have like a scheduler that they use to run jobs against an on-prem cluster, right? They create some input model data, and then they submit it against a cluster. It goes to a queue, it waits for some time, and then the simulation is completed. But again, there's a lot of unknowns here, right? Has the engineer been trained to use the right hardware selections, the right software selections, the right precision to run the job? What happens to all the data after it's actually being computed? Is it being securely handled? Is there backup of data? So there's a lot of unknowns here. With intelligent computing, everything is available on demand and provided in context, right? So researchers are now focusing on solving their problems. So you're able to get the R&D context. You can guide your engineers, hey, what you need to use, which software, which versions. You can set up templates for their workflows. The IT and HPC context, all those kind of different hardware and software filters can be set up, which are consistent with internal IT HPC policies. From a business and technology perspective, you have full insight into how you're utilizing the platform, how you're utilizing multi-cloud or even hybrid deployments, right? So everything, again, is always available on demand, always in context. Data is being backed up. So that's actually helping you to actually intelligently meet your R&D objectives. And then finally, last slide before we jump into the demo. Also, what this means, why should you as an engineer be looking at the cloud today, right? Maybe you already have an on-prem cluster. So one of the primary reasons is flexibility and scalability, right? Typically on-prem, you have that one specific hardware which is utilized for any type of workload, right? Whether you're running a CFD workload, whether you're running a combustion workload using Converge, or you're running a mechanical analysis, all those FE analysis, all those different tools are using the same hardware. So it's not really optimized per tool that you're running, right? Again, the other thing is you have a queue because you have limited resources that you can use. So the jobs are usually queued in time. But when you come to the cloud, the key differences are one, the resources are available on demand, so you can submit multiple jobs at the same time. But even then, the resources themselves can be optimized per workflow, right? So if you want to run a big combustion analysis with Converge, you can choose an architecture that has a high interconnect speed, right? Some of the InfiniBand options that we have on the platform. Or if you're running a smaller model, you can then probably take advantage of something just with high clock speed if you're not running in too many nodes. So you can optimize for performance as well as cost there. So those are the primarily, the two main advantages that you get for your workflows when you run them on the cloud. So with that, we will jump into the demo. So for the demo, we'll be going through this PFI port fuel injection model that Converge provided for us. And like I said, for the hardware, we'll be actually running this on some of the high interconnect speed hardwares that we have with around 100 Gbps for a couple of different options here, as well as you can see one with 200 Gbps in there as well. And these are all from different cloud providers that are accessible on the platform. So with that, actually, let's jump into the demo. So for those of you who are new to Rescale, the first time you want to sign up for an account, you go here to rescale.com and you can hit sign up and create an account. Once you have created an account, you can log in and it will take you to so this is the Rescale platform. This is where all the orchestration, all your submission, everything happens. So once you log into the platform with your account, you're directly taken to the jobs page where you get access to all the previous jobs that you have run, or any job that's currently running. So you can see I actually have a Converge job executing at the moment, right? So this is usually where you spend most of the time on the platform. Now let's take a look at creating a Converge job from scratch and submitting it on the platform, right? So we'll start off with creating a new job. So just hit the create new job button here. Let's give the job a name, Converge demo. And really the 3 steps that you need to take to submit a job. So this is where I mentioned, the streamlined interface without any of the complexities being visible to the user, right? The user, all they need to do is create a job, upload those input files, choose the software, the version that they want to run with the license settings, and then choose the hardware that they want to submit it against. That's all you need to do. You have an optional post-processing step if you already want to do some default post-processing after your simulations are completed. So you have the option for input files to add from cloud storage or even add from this computer. So you can browse to your local computer or add from a storage device if you have launched that previously. So for this example, I already have the files in cloud storage. So I'll choose cloud storage. And under here in Converge, I have the zip file, which is the which is the model that we're going to use today. So this zip file contains all the input files for this Converge model. So I've already zipped it locally and I've uploaded it into the platform. And you can see that it will already be decompressed automatically once it reaches the cluster. So that's pretty much inputs. Then we can go to the software selection page. Here's where I mentioned we have the 600 plus softwares available to you. Obviously, today we are going to be working with Converge 3.0. So you can see here, Converge 3.0 is right up the top. I'll choose Converge. After you've chosen the software, you're going to choose what version, and we maintain all the legacy versions as well as the latest version on the platform. So let's just choose the latest version here. From a command perspective, this is also completely abstracted, so you do not need to change this at all. The system automatically will run this across how many ever nodes you select in the next step on the hardware settings page. Again, if you want to do some custom commands, you have that option to edit it here, but again, it's set up in a way that the user has to minimally interact to submit the job. So the command can be left as, and then you come to the license option, right? Like I said, Converge is one of our Convergent Science is one of our partners which provides on-demand license usage on the platform. So you have the option to pay per job on the platform once you're authenticated from Convergent Science. You also have the option if you have an on-demand, if you have an existing license, say on your on-premise cluster, sorry, on-premise network, then we also can set up a connectivity to that license, so you can actually just put in your local converged license, the RLM license settings, and you can connect to that license server as well. So for this, we're just going to use the use on demand license option. So we completed inputs and software, and finally the last step really is to specify the hardware settings, right? So here is where you will get access to all the different HPC shapes, right? So I mentioned about simulations, these kind of CA simulations needing specialized hardware. So all the hardware that you have seen here these are the specialized HPC hardware that's provided by the cloud providers, right? So this is a mix of different cloud providers in here, and you can see they're also categorized as different, different categories, right? So you can see general purpose ones, high interconnect, high memory, high clock speed, high disk, and so forth. Now, for Converge, typically if you're running large models, of which this is an example, you want to use something with a high interconnect speed, right? So we're going to use Carbon here, which is one of the most performant core types that we have for Converge. It's also a Skylake processor with a high clock speed, and it has high interconnect speeds as well. So once you've selected the core type, now you have the flexibility of actually scaling up your model, right? Really running it on as many cores as you want. You're not limited by any hardware resources that you need access to, right? So you can really run it on as many cores as you want. You can see here that one node of Carbon comes with 44 cores, so it will go in multiples of 44. For this demo, let's just submit it on 2 nodes. So I have 2 nodes here, which is pretty much exactly 88 cores. And we can select the wall time that you want to submit the job for. I'll just leave it at 6 here. And finally, your options are either you can save the job, you can save it as a template, so you just save the settings and you can reuse it, or you can finally just hit submit to submit a job, which is pretty much what I'm going to do here. So once you hit the submit page, it takes you to the status page, which is within the same interface, and it gives you the status of how the simulation is proceeding, right? So in the interest of time, I'm going to switch over to the previous job that I already have running here. So here you can see this job has been running for around 3.5 hours now. It's the same job that we just submitted today, right now, just previously. And this is when the cluster runs, and this is when the simulation is being executed. Now, once the simulation is being executed, we provide a live tailing interface, so you can actually tail the log files that you have to identify, hey, is my simulation converging? Is it diverging? Do I have to make any changes? So forth. So you'll have all the different input and in and out files from your Converge simulation that's in the shared directory already here that you can track. And you'll also have the process_output.log file, which will give you, the status of the simulation itself, right? So here you can see it's reached around 40–50% of the number of cycles. Now this was just submitted on 2 nodes, so you can use that approach to actually tail your job and look at the log files as well. Now we also provide additionally an in-browser SSH option. So this is useful if you have, if you're Linux savvy and you really want to make some quick changes to some of these files on the run, then you have the option to just use an in-browser SSH and change some variables or some values during your simulation. So for example, here, if I look at the work and shared folder, I can see that I have access to all the different input files that I uploaded, also the output files that are currently being processed against on that cluster. So this is like a Linux interface directly to the running cluster. And then finally, you have the job logs, right? So once this job is completed, you will see the results section upload with all the results files. So let's actually go back now to one of those jobs that completed, right? So you saw that this job was run on two nodes, 88 cores. I ran the same job on 484 cores. Then this comes to the scalability factor that Samira mentioned. And you can actually see that this job on 484 cores, which is around 11 nodes of Carbon, actually completed in under 2 hours, right? So we previously saw that on 88 cores, it was still around 40% in 3+3.5 hours time. So that comes back to the scalability aspect of the software, as well as the access to those large number of clusters on the platform. Now, going back to the results here, so once the simulation is completed, all the results are transferred back from your, from that shutdown cluster to your Rescale storage. And here is where you'll have access to all of those, right? So now you can select all the files and you can download them directly from here. Now, we usually get a question around, best practices for file transfer, data storage. So we have a lot of options, rather than just using a web-based download, we also have dedicated transfer clients for Windows, as well as a programmatic access, which will give you faster download speed. So there are a lot of different options around there as well to manage your data, especially some of these simulations will throw out a lot of gigabytes of data. So we have options around that as well. Now, the last thing I wanted to point out is some options for post-processing on the platform. Now, if you don't want to additionally move and transfer data locally, you also have the option to just visualize these results using virtual desktops on the platform itself, right? And that's the last point I kind of want to go over. So we looked at batch jobs. We looked at how we can submit batch jobs, how we can take advantage of massive clusters to scale up those jobs on the platform. Now, going to desktops, this is where you can actually launch virtual desktops and use remote desktops to actually post-process on the platform. So now you can see actually I already have one launched with Converge Studio, which we'll take a look at. But again, the step to create a desktop is exactly the same as a job, right? So you can just give it a name. Let's just leave it as Converge here. So you can see here you have TechPlot as well as Converge Studio. So if you want to do more than just line graphs, you can use the TechPlot option for doing visual post-processing as well. Once you have chosen the software, here you'll get an additional jobs page. And here is where you can actually attach any completed job to your desktop, right? So you will have access to those files once your desktop has launched. And finally, you get the option to select what kind of machine you want to run it on, right? So we have different machines. We have machines that have GPU if you want to do some, creating some animations or rendering some output files. Or we also have, basic Linux desktops as well as basic Windows desktops, which are all different options for you. So again, I already have one launched here. So let's actually take a look at that one. So here you can see that I actually attached Converge in here, and I attached that completed job as well. So this is exactly like a Windows machine, remote Windows machine. You'll have Converge Studio up here in the shortcut menu on the desktop, and you can just launch it directly and attach it to the jobs that you have. So here I have already that job that I attached is in the Z drive. Attached jobs. This is the webinar completed job, and I have all the output files in here as well. So this is just selecting the directory. So I'll just select the directory as output. Yep, and then you can select, the different plots that you want to look and, visualize your simulation output to the post processing. And again, if you want, you can launch TechPlot as well to do more, 3D visualization and post processing as well. And once you're completed with this, you can just come back to the platform and you can shut down that job. First hit sync files, and any new file that you have created will be synced back to the storage for that job. So you'll have those files even after the desktop is shut down. So that's most of what I wanted to cover, and I think we have around 11 more minutes. So I covered batch desktops. I covered the batch workflow, how to run batch workflow, and how to use desktops to do some post processing. So that brings me to the conclusion of the webinar, what I had planned. So we'll take up any questions now. Over to you, Julie.
Perfect. Thank you so much, Nathan. Appreciate it. It looks like we do have a few questions rolling in here. The first one is from Arpita. Is it feasible to run custom builds of Converge 3.0 on Rescale?
Yep, that's a great question. So yes, we have a lot of customers who use their custom builds of Converge 3.0. So it's a very easy process. All you need to do is actually along with your input files, actually just upload those binaries for your custom version. And on the command line, you can actually use those. You can point to that custom binaries that you'll be uploading, and then you'll be able to use those custom binaries to run those custom versions on the platform. And we have made it to self-serve, so you do not need to wait for us to onboard anything. You can directly use the Converge 3.0 option and just upload them as binaries.
Okay, it looks like we have another one in here. This one is from Jacob. I typically use Python or Bash scripts to interact with our local HPC cluster. Does Rescale provide any options for programmatic submission?
That's another question. Good question. So yes, so what we saw today is primarily the GUI. So we saw the GUI approach, but what we do have is a dedicated command line interface as well. We call it the Rescale CLI, where we have a dedicated mechanism in which you can set up an input script and you can submit that job like from a terminal or from a command prompt interface, and directly authenticate and submit the job end to end without even needing to log into the platform. Yes, so we have options for programmatic submission as well.
Great. So again, just a reminder, if anybody has questions for either Samira or Nithin, now is the time to ask them. I just see one more in the queue, and then maybe we'll give you a few minutes back if I don't see any others. This one says, it's from John. What are some of the best practices around data storage and transfer?
Yep, definitely. So going back to that, I touched quickly on that. So like I mentioned, a lot of these simulations will throw up a lot of huge data sizes. So the best practices around that is if you're using the Windows, if you're using a Windows machine, then rather than using the web-based download, you can use what we call Windows Transfer Manager.
Okay.
Yep. So we have the Rescale Transfer Manager, which is a dedicated client that you can download onto your platform. And instead of using web-based downloads, you can use this client directly, and it will actually speed up your downloads a lot faster. And then going back to the command line interface, we also have direct downloads using the command line tool, which is also accelerated downloads and transfers compared to the web interface.
Okay, fantastic. It looks like we don't have any more questions, so we can go ahead and wrap up this webinar. Special thanks again to Samira and Nithin for presenting for us. And just a reminder that you can find information about any of our other upcoming webinars on our social channels, as well as the popular Big Compute podcast at bigcompute.org or wherever you get your podcasts. So thank you for joining us, and have a great rest of your day and stay safe out there.